Yeah, thank you for the introduction and thank you for organizing this wonderful seminar. I'm Xin Chen. I'm an assistant professor at Texas A&M University, and it's my great pleasure to share our recent work on data-driven coordination of IBRs. And first, I have to thank my collaborators, Professor Na Li, Professor Jorge Poveda, Professor Changhong Zhao, and my PhD student, Xiaoyang. A quick introduction about my group. So my group is called SPEED, and our research lies in the intersection of optimization, machine learning, and control theory for smart power and energy systems. And we focus on three main research topics. The first one is the large-scale high renewable power system optimization for system planning and operation. The second one is autonomous coordination of flexible distributed energy resources. And the last one is the data-driven, physics-informed dynamics modeling and adaptive control of IBR systems. And we aim to develop scalable learning-based control and optimization theories, algorithms, and tools to address those problems. And in today's talk, I'll focus on the last topic, the coordinated control of IBRs. In recent decades, driven by the climate change and energy sustainability, electric power systems are undergoing a profound transformation with a fast proliferation of power converter-based resources like wind turbine, solar panels, batteries, and electric vehicles. I guess many of you have seen this picture maybe many times. And this picture is from the UNIFI website and illustrates the transition of our systems. In the past, our system was dominated by synchronous generators. At present, we have the grid has witnessed a large-scale integration of IBRs, and most of them are grid following. But in the future, our system will be dominated by IBRs and with a mix of grid forming and grid following inverters. They have very different dynamic behaviors, and they will fundamentally change the power system dynamics. But the good thing is the large-scale IBRs can provide enormous power flexibility with very fast response capability, which can be harnessed to enhance the power system operation. So then a fundamental question is how to coordinate large-scale IBRs in the power grid. When talking about the grid level coordination, here is the structure used in today's power grid. And according to the different timescales, we separate into the slow timescale optimization and fast timescale control. And in the optimization layer, based on the predicted disturbance, we perform the grid level power dispatch to determine the optimal operating set points, like the unit commitment and the economic dispatch. Then in the fast timescale control, we have a closed loop feedback control system to handle the real-time disturbance through voltage control and frequency control. And in the optimization layer, the goal is to achieve economical efficiency and ensure steady state power balance and satisfy the power system operation constraints. And for the fast timescale control, we aim to maintain system stability and stay robust to the time-varying environments. However, the integration of large-scale IBRs, they lowers the system inertia and leads to fast system dynamics with continuous disturbance. As a result, we need fast power dispatch and response to adapt to the fast changing system conditions. As a result, this timescale separation boundary blurs, and an interconnection between the optimization and the control layers becomes necessary. And to do this, One solution is the stability constraint optimization, which aims to integrate the transient stability criterion into the optimization and into the grid level power dispatch. And another promising solution is the optimal system level control that aims to integrate the optimality and power system operation constraints into the control layer, so that we can achieve both advantages. And in this talk, we will focus on the optimal system level coordinated control of IBRs. But this task is challenging. So the first challenge is the scalability issue. So this figure shows the transition of power systems of the Denmark grid. We can see that it changed from a number of central power plants to numerous small capacity distributed energy sources. So the key challenge is how can we coordinate a large number of like millions of heterogeneous IBRs in large-scale power network with only limited communication and computation resources. A promising solution is we can transform the centralized control into distributed control. In this way, we don't need a control center to collect the information from everyone and solve a large-scale centralized system-level coordination problem. Instead, in the distributed control, each IBR aggregator only needs to perform their own computation and coordinates through the communication with their neighbors, so that we can enhance the scalability of coordination and also preserve the user's privacy. The second challenge is the unknown model. Because of the complex physical power system dynamics and the uncertainty of renewables and load, it's becoming very challenging to build and maintain accurate power system models, especially for the real time. In addition, the IBR dynamics model may not be known to the grid operators because the internal IBR control information is proprietary and not disclosed by the manufacturers. So then how can we address the unknown model issue? One of the biggest opportunity is to use the explosion of data. And in recent decades, many smart sensors and measurement units and with upgraded communication technology have been deployed to the power systems, which makes real-time monitoring and control available, so that we can develop data-driven and AI-based decision-making schemes to address the unknown model issue. And in summary, so we aim to address two fundamental challenges. One is the scalability issue, and the other one is the unknown model. What we do is we want to develop distributed data-driven control schemes to address these two challenges. And a key idea is that instead of just applying existing algorithms, we want to leverage specific problem structures and our domain knowledge to design the algorithm so that we can achieve high performance guarantees. And in this talk, I will give you two examples to show how can we coordinate large-scale IBRs for the system-level optimal control. So one is for the voltage control, and the other one is for frequency control. And the key idea is we want to develop data-driven and distributed control schemes to address the unknown model and scalability issue. And we want to leverage the specific problem structures for the control design. Okay, then let's dive into the first part, the voltage control. We studied the voltage control in distribution systems. And for example, in a distribution feeder like this figure, if there are two loads here, then the power will flow in this direction to supply the load, and along with the power flow direction, the nodal voltage magnitude will descend. which may violate the lower voltage limits and cause the undervoltage problem due to the heavy load. And on the other hand, if we have a solar generator here, then we may have reverse power flow and a rising voltage level, which may violate the upper voltage limits and cause the overvoltage problem due to large-scale renewables. Then what we want to do is we want to control the power injections of flexible IBRs, like the battery, EV charging, the PV panels, so that we can maintain the nodal voltage profile stay in this safety interval. So then let's formulate the real-time optimal voltage control problem. This is a distribution system. The blue nodes represent the flexible IBRs. Suppose there are n IBR units in the system and with communication links across them. From the control perspective, the distribution system takes in the active and reactive power injection P and Q of the IBR units and the disturbance D as the inputs. And the output is the voltage measurements V. And the voltage measurements can be used as a system feedback by the IBR units to control their power injection. So it forms a closed loop system. And in this case, for the distribution system model, we can use a static input-output mapping function, VXD, to represent the system model. And from the inputs of power injection X and disturbance D to the voltage V. So here, this is an approximation by using the property that the power system voltage dynamics can converge very fast. And then for the voltage control problem, it's like this. So once a disturbance occurs, we want to control the power injection of IBR units so that the system level voltage magnitude will be restored back to this safety interval. And this is the problem we study. But for this one, we need to address 3 key challenges. The first one is the requirements of optimality and safety. So we can formulate this using this optimization problem. So the OVC optimization model. So in this model, the decision variable Xi is the power injection, active and reactive power injection of IBR units. And in the objective, Ci is the cost function, which used to model the renewable curtailments and load shedding costs. So the objective is to minimize the total system level total costs. And then for the constraint, the calligraphic Xi is the power capacity feasible set, which used to model the maximum power generation and also the inverter current limiter. In addition, we also have the voltage limit constraint. So this model defines the optimal control decision X star. And once we can achieve X star, we can achieve optimality and safety. So the goal is that we want the closed loop system can autonomously drive the control power inputs into this optimal solution so that we can attain optimality and safety. And second challenge is the scalability issue. So as we mentioned before, we may have thousands or even tens of thousands of IBRs to control in the same time. So we need a scalable coordination scheme. And the next challenge is the unknown model. And in our case, that means this input-output mapping function, VXD, is unknown. Because this function actually captures the entire distribution system information, including the network topology, the line parameters, the nonlinear power flow equations, and the unknown real-time disturbance D. So all those information are often unavailable in practice. So here we think this mapping function VXD is unknown. Then the question is, under these three challenges, how can we design the coordinated control for the IBR unit? Our key solution idea is the feedback optimization. And it turns out that the voltage control involves a general structure for the real-time control of complex physical systems. And specifically, in many applications, we may have this problem structure. We have a physical system that can be represented by very complex physical system dynamics. And the physical system takes in the control input U and disturbance D, and output is the feedback X that can be used by the controller to design the control law. And control law can determine the optimal input U. And we want the closed loop system can drive the system state and control to an optimal steady state that can be formulated by an optimization problem. And key challenge is that in many cases, the physical system is very complex and very hard to model, so that we don't have the physical system model. And also we don't know what is the real-time disturbance D. And then under this condition, how can we design the optimal control law such that the closed loop system can achieve the optimal steady state? So the key idea is the feedback optimization. And we want to design the control law such that by using the system feedback, the combination of the physical system dynamics and my control law behaves like an optimization algorithm. For example, the primordial gradient algorithm that solve the optimization problem. So in this way, and this is the idea of feedback optimization, and different from the regular optimization problems with given parameters and solved offline. The feedback optimization is implemented in real time. And every time when we need the system information, we can just take the system feedback or the system measurement as the input, so that by using the system feedback or measurement, we can get rid of the physical system model information. And we can also achieve the optimality because that will converge to the optimal steady states. And let me take the voltage control problem as the example to show how can we do that. So this is the previous optimal voltage control framework. And we also built this optimal voltage control optimization model that describes the optimal solution X star. And then when we want to design the optimal control law for the IBRs, then to do that, we start from the OVC optimization model. And what we can do is we can introduce the dual variable lambda and then build this saddle point problem. Then we can use projected primordial gradient dynamics to solve the saddle point problem. So in this dynamics, the first equation is the dynamic updates for the primal variable x, which is the power injection. And then the second and third equations are the dynamic updates for the dual variable lambda. And in the first equation, the Li is defined as this equation. Although this looks complicated, but you can just view this dynamics as an extended version of the gradient descent for solving constraint optimization problem. And here the lambda and projection is used to guarantee the constraints can be satisfied. So then, since this is a solution algorithm, we can take this solution dynamics as my control law to control the power inputs of IBR units. Because eventually, since this dynamics is a control law, it can converge to the optimal solution defined by the OVC problem. However, this algorithm cannot be implemented. It's not implementable because of the unknown system model. And specifically in this dynamics, we can see that we need the voltage function Vxd and also the partial derivative dVj dxi. And all those terms need the system model, but which are unknown. So how can we address this issue? So our idea is for the function VXD, we can just replace the function value VXD by the real-time measurement. Because this algorithm is implemented in real time, so the measurement is actually the natural system response or the natural function evaluation for the function value VXD. It's like every time we implement the X and the D, and once we want to get a function value, the physical system can help us to do the calculation. And what we do is we can just take the voltage measurement as the function value. And so that we can replace the unknown voltage function value by the real-time voltage measurement. And for the unknown partial derivative, we can use the zeroth order to estimate the gradient. So the zeroth order is that we have a unknown function Vx. Once we have an input X, we can output the function value V. So then we can add a small perturbation, a sinusoidal perturbation, A sin kappa t, to the input. And then it will output the perturbed function value. And once we have the perturbed function value, we can form this zeroth order estimation. And this part is the estimation of the first order gradient. And only using the function evaluation or the measurements. And we can replace this part using the real-time voltage measurements. And in this case, we can use the zeroth order gradient estimator to replace the partial derivative in the dynamics, so that we can get rid of the the unknown system model. So by combining these two solution ideas, and this one is our proposed projected primal dual zeroth order dynamics. And for this dynamics, is implemented for every IBR unit. And it has three parts. The first one is the previous projected primal dual dynamics. And the second one is the zeroth order gradient learning dynamics to learn the gradients based on the voltage measurements. And last one is the dynamic average consensus, so that we can achieve distributed control. Every IBR unit only needs to communicate with their neighbors. And to implement this dynamics, the input we need is the local voltage measurements and also the local communication with neighbors of a scalar value, the YJT. The YJT is the communication variable. And then by running this algorithm, we can determine the optimal, the power reference set point and implement this in the real system. So combining with this voltage control framework, what we can do is we can take this proposed projected PDZD as the control law for controlling the IBR units. And in this case, each IBR unit only needs the voltage measurements, and that can update the power injection and implement it to the system. So this is our proposed optimal voltage control law for coordinating IBRs in the voltage control problem. This is the control process illustration. So in the physical layer, we have multiple IBR units. Then each unit only need to take the local measurements of the local voltage and communicate with their neighbors of a scalar variable YT. And then after updating using my algorithm, you can implement the local power injection action X hat. And then the system will respond to the power injection and present a new voltage profile. So it forms a closed loop system. And in this way, we can achieve optimality and safety in a model-free and distributed fashion. So by model-free, when we implement this algorithm, we don't need any system model information. We only need the real-time measurements. And by distributed, we mean that each IBR unit only needs local measurements, local communication, and local action. We don't have a control center to organize everything. And to achieve that, the key idea is we combine the real-time physical system feedback and the zeroth order gradient learning. And we also have the theoretic guarantee. So we prove that our proposed algorithm can achieve asymptotic stability and is structural robust to the small measurement noise. So if you are interested, you can read our paper for more details about the theoretical analysis. Then let me show you some simulation results. So we tested our algorithm on a three-phase IEEE 69-bus distribution system. And to do that, we built a MATLAB Simulink model. And for each model, we have in the Simulink model, we can control the distributed generator and the PVs for the voltage control. And the control variable is the reference value for the active power P and reactive power Q. And for the PV module, we have a high fidelity EMT inverter model. So although in the previous theoretic derivation and analysis, we consider a linearized and a simple model, but in the simulation, we are using the high fidelity EMT model to test the algorithm. And the upper figure is the PV inverter inner control loop. And the lower figure shows the implementation of our projected primordial zeroth order control algorithm. So this is the simulation setup. And in the first case, we simulated a step power disturbance. And we can see that initially, the voltage is below the lower limit, 0.95. Then after implementing our algorithm, it can restore the voltage back to the safety interval, and all the voltage are above 0.95. And the lower figure shows the power outputs of the flexible IBR units. We can see that after about tens of seconds, the power output can converge to the optimal value. And it will always satisfy the power capacity upper limits and lower limits. And in the second case, we simulate the continuous power disturbance by injecting the real-time time-varying solar generation. And this solar generation is from the real-world solar generation profile. So we use the time-varying solar generation to simulate the disturbance in the system. And here, the upper figure shows the case, the voltage profile, when we don't implement the voltage control. We can see that the voltage magnitude violates the upper and lower limits frequently. And the lower figure shows the case when we implement the voltage control. And we can see that we can effectively maintain the voltage profiles within the safety interval in the second case. So in summary, in this work, we proposed a projected primordial zeroth order method by combining the feedback optimization and zeroth order gradient descent. And the combination of the physical dynamics and my control law behaves like an optimization algorithm to solve the optimal voltage control problem. And this algorithm is actually general and can be applied to many real-time model-free optimal control problem for the complex physical systems. And we can address the unknown system model issue and the scalability issue and guarantee safety and have the convergence performance guarantee. And this algorithm can also be used in many different applications like the building control, the wind farm control, source seeking, and more. So that is for the first part. We coordinate the IBRs for voltage control. And then let's dive into the second part. How can we coordinate IBRs for frequency control? So in power systems, frequency is the most important indicator for power balance. And once disturbance occurs, the power imbalance will drive the system frequency to deviate from the nominal value. And then we have a hierarchical frequency control framework to restore the frequency and eliminate the power imbalance, which includes the primary, secondary, and tertiary frequency control. And the tertiary frequency control is the economic dispatch, and those control mechanisms are performed at different time scales. But in the future, converter dominant grid, we have a different story. The large-scale integration of IBRs lowers the system inertia and leads to very fast system dynamics. But the good thing is we have more controllable IBRs, and they can provide enormous power flexibility with the fast response capability. But to coordinate IBRs for frequency control, we also need to address the many challenges like the heterogeneity, the scalability, and unknown system dynamics model. So then the question is, for the future converter dominant power grid, is the current hierarchical frequency control framework still applicable? And how can we coordinate large-scale IBRs for the system level, for the grid level frequency control? And specifically, we want to optimally coordinate IBRs by controlling their power set points for the frequency control. And here we have 4 control goals. The first one is we want to achieve primary, secondary, and tertiary frequency control in real time. That means we want to stabilize frequency, restore the nominal frequency, and achieve economic dispatch all at once. And second goal is we want to satisfy the IBR operational limits and the power network constraints. And next one is we want to design a distributed control mechanism so that we can enable scalable coordination and preserve the privacy of IBR units. And last one is we want the algorithm can be model-free so that we don't need the unknown power system dynamics model and the real-time disturbance information. So this is the these 4 control goals in this work. And first, we want to formulate the problem. And in the problem, we consider a power system with a mix of synchronous generators, grid-forming inverters, and grid-following inverters. And for the synchronous generator, so we can formulate the swing dynamics using this equation. And here, the Mi is the generator inertia. The Di is the damping coefficient. Omega I is the frequency deviation, which is the actual frequency minus the nominal frequency. And Pig is the mechanical power, and Pi is the actual terminal output power. So this is for the synchronous generator. And for the grid-forming inverter, here is the linearized dynamics model. So here we consider a Joule-based grid-forming inverter. The KIM is the Joule gain, and this part is the low-pass filter, and alpha I is the cutoff frequency, and PIM is the power set point, and the PI is the actual power output. And for the grid, and we can equivalently reformulate this equation using the state space form and as this equation. And in terms of the grid following, and we have this equation. The Pi is the actual terminal output power. The PIL is the power set points, and the KIL is the Joule gain, and omega I is the frequency deviation. And this is those are the equations for each component. And then from the system perspective, and we have a power grid. And for this power grid, for each bus, the Pi is the power input from each component, and Pij is the power flow from the node I to node J. And here we use the DC power flow dynamics. And the Bij here is the line coefficients. and theta I is the phase angle of node I. And in addition, we have the nodal power balance as this equation. The Pij is the branch flow from node I to node J. And here the Di is the uncontrollable net load, and it captures the disturbance. For example, if we have an uncontrollable load or uncontrollable renewable generation change, it can be reflected in the Di term. And these are the dynamics equation for the overall system. And then when we look at the grade level coordinated frequency control, we have a physical system, and we want to design a distributed optimal control law to control the synchronous generator, grade forming and grade following inverters. And according to the previous modeling, we can represent the physical system dynamics using those equations. And those equations are the previous equations by eliminating the power outputs and combining with the power flow. So we have the corresponding equations for different components. And then from the control perspective, the physical system dynamics will take in the power set points, PIG, PIM, and PIL. All those are the power set points for the generator, grade forming and grade following inverters. And that will taken as the inputs as well as the disturbance Di. Those are the inputs for the physical system dynamics. And the system output can be the measurement of the frequency deviation omega I and the power flow Pij. Those information can be taken as the system feedback for the control law. And the question is, we want to design the distributed optimal control law to coordinate different components in the system. And how can we design that? So for the frequency controller design, we use the similar idea based on the feedback optimization. And first of all, we formulate this optimal frequency control optimization model. So for this model is essentially the economic dispatch model. And the objective, the decision variable is the power set points, PIM and PIL. Those are the power set points for grade forming and following inverters. And in this model, we didn't consider the synchronous generators because the inverters have the faster dynamics. But we can also incorporate the synchronous generators into this model. And then the objective is try to minimize the total system level control costs. And the first constraint is the power capacity constraint for the power injection of inverters. And then the second, third are the DC power flow equation. And last one is the line thermal constraints. So essentially this model is the economic dispatch model. And then this model defines the optimal control decision for the grade forming and grade following inverters. And then what we do is we want to modify this model a little bit by adding the frequency omega I variable and some auxiliary constraints so that we have a modified OFC model. And the difference is that we have additional components from the frequency deviation, and also we add two power flow constraints into this model. So why we need a modified model and why we design this way, and you will see that later. So this model is carefully designed for the following purpose. But we can prove for the new model we have the same optimal solution. That means the PIM star and PIL star are the same as the original OFC model. They have the same optimal solution. And in the new model, the optimal value for the frequency deviation is 0. So that means we have the equivalence between the previous model and the modified model. And for the modified model, the optimal frequency deviation is also 0. So then we can introduce the dual variable lambda and solve the modified OFC model using a projected primordial gradient algorithm. And this is the mathematical formulation of this projected primordial gradient dynamics algorithm. And for this algorithm, you can just view this algorithm as an extended version of gradient descent for solving constraint optimization problem. And this algorithm can be separated into 3 parts. And then we are surprised to find that the first part, the dynamics in the solution algorithm, is exactly the physical power system dynamics. And the remaining 2 parts can be taken as the controller for the grade forming and grade following inverters. And why we have this coincidence is because in the previous step, we carefully designed the modified optimal frequency control optimization model so that we can achieve this property. And this is by using the specific problem structure. And then in this case, the physical system dynamics and these 2 controllers will generate the set points PIM and PIL for the system. And the system dynamics will take in the disturbance and power set points as the input. The output is the measurement of frequency deviation and power flow PIJ. And to implement this algorithm, we also need a local communication of lambda, the dual variable. And because the closed loop system, by combining the physical system dynamics and my controller, behaves like a primordial gradient algorithm to solve the OFC model, so that the closed loop system will autonomously drive the system state and control inputs to the optimal solution, the PIM star, PIL star, and eventually the frequency deviation will be 0. And in this case, we can achieve the optimal control decision, and we can restore the nominal frequency because the frequency deviation in the steady state is 0. And in this case, it's a distributed control because every grade forming or grade following inverter only need local measurements of the voltage of the frequency and the power flow and local communication with their neighbors. And in this case, we don't need the system model because for the first part, the system dynamics, this part can be implemented by the physical system. And it's like we outsource the first part dynamics to the physical system, and the physical system will help us to do the calculation. What we need to do is just take the measurements, and that is the system feedback after performing the dynamics. And this is the illustration of the overall control process. And in the system, we may have different components, and every component just measure the local frequency deviation omega I and the local power flow PIJ. And then in the separate layer, they can communicate a dual variable of lambda with their neighbors. And after updating using my algorithm, it can implement the local power set points. And it forms a closed loop system. And combining the control law and the physical system dynamics, it will drive the system states and control inputs to an optimal steady state. So the key to achieve that is we leverage the real-time system feedback and the physical system dynamics structure. And for this algorithm, we also have the theoretic guarantee, and we proved the algorithm has asymptotic convergence and also a good dynamic tracking performance. Because if we have a time-varying system, then this algorithm can track the optimal solution, and the tracking error is bounded by the initial difference and the system modeling error, and as well as the shifting the shifting rates of the system. And then is some simulation results. So we implemented the simulation using the power system toolbox. Although in the previous discussion, we only used the DC power flow, and we consider very simple synchronous generator model and inverter model. But in the simulation, we are using very high fidelity components for the generator and for the inverters. And for the first one, in the first case, we also simulate a step power change. So then we compare the case using and without using the frequency controller. Without using the frequency controller, by the local Jupe control, it can stabilize the frequency, which is the red curve, but cannot be stored to the nominal frequency. And using our algorithm, we can not only stabilize the frequency, but also restore the frequency to the nominal value. And figure 2 shows the overall control cost. So as the system converge to the optimal steady states, the control cost will also converge to the optimal control cost. So that means we achieved optimality and safety. And second case is we simulate a continuous power disturbance. And figure 3 shows the time varying PV output as the power disturbance. And figure 2 is the frequency dynamics comparison. The blue curve is the case we use the optimal frequency controller. So we can see that the the controller can stabilize the frequency. So so for future work, this is our future work in terms of the theory and application. So for the theory, we want to incorporate the available system information into the algorithm so that we can combine both the model information and the data-driven algorithm. And in the application, we want to test the algorithm in the real world microgrid and distribution system. So we want to implement the algorithm in the real world power grid to see what's the actual performance in the real system. So that is all for this work. And thank you. And feel free, if you have any question, feel free to ask.
Yeah, thank you so much for the presentation, Xin. That's